Hi, it's my pleasure to present to you today our work on the transformation of ontology-based conceptual models into relational schema. I'm João Paulo Almeida, and this is a paper co-authored with Gustavo Guidoni at the Federal University of Espírito Santo, and also in cooperation with Giancarlo Guzzardi, who's at the Free University of Bolzano and the University of Twente in the Netherlands. So basically, we were motivated in this work by our need to implement or realize conceptual models, and in this case here, realize them in relational schemas, so to have data concerning the domain of a certain conceptual model. And the barrier that we need to address here is that there is a mismatch between those primitives we use for conceptual modeling and those primitives that are used in the relational schema, in the relational model. These are often called the semantic gap or the impedance mismatch. So that we need some kind of strategy to transform those different primitives, or realize those abstract conceptual modeling primitives into those more concrete primitives of the relational model. So a number of strategies have been proposed in the past to cope with, especially with the presence of the specialization or inheritance hierarchy in the object-oriented based conceptual models. This has often been accommodated in object relational mappings, in object-oriented programming languages, and because of the influence of object-oriented programming, there have been conceptual modeling mechanisms that have been ignored or that have not been given attention. And for us, these are very important to be able to build conceptual models of high quality. These include multiple inheritance, often neglected due to programming or realization considerations, orthogonal specialization hierarchies, which are a powerful mechanism to build more concise conceptual models and reusable, and also dynamic classification, in which objects can change during their life cycles and change the types that they instantiate. So the dominant strategies in the literature include those three here and variants of those three strategies. So they all have their problems, sometimes not supporting or poorly supporting one of these mechanisms that we need to support from conceptual modeling. Or even when they do support those mechanisms, which is the case of the one table per class strategy, we have some performance problems, either in terms of dynamic classification performance or even in the most basic primitives, primitive operations that we need to do on data. So for example, in the one table per class strategy, we need to do a lot of joins, and there are a lot of tables affected even in reading or writing operations. So we have observed, because we have been doing a lot of work with ontology-based conceptual modeling languages, and these ontology-based conceptual modeling languages like OntoML have certain or incorporate certain ontological distinctions that allows us to realize that not all classes are the same. So there are different types of classes, and we can explore those differences to guide this realization and the transformation. So here we have the running example that we also use in the paper, which is a UML class diagram enriched with those additional stereotypes from OntoML. And these will be able to guide us in the transformation process. So first we realize that there are those things called kinds here. These are object kinds, and they form the basic way to partition the objects of a domain into those classes here. So they are our way to identify objects in our domain. And then we have those types, which actually are they are supertypes of kinds, or they classify entities of different kinds. So here we have customer classifying both persons, and organizations, and a named entity classifying persons and organizations. So, objects of different kinds are in the extension of those things that we call non-sortals, which includes the categories here and the row mixins. And then we have those classes which are specialized kinds. So now they take kinds and create special ways to classify those kinds. So here we have a number of orthogonal generalization hierarchies, for example, partitioning persons according to their life phases, or classifying persons in different ways based on their citizenship, based on their participation in certain relationships, or based on some properties that they have. So here I have all kinds of generalization sets with different variations of covering and overlapping generalization sets and so on. So our approach is, instead of having one table per class, or one table per hierarchy, or one table per leaf class, we realized that we could use those ontological distinctions and then propose different kinds of strategies. And the strategy that is promising in our view is the one table per kind strategy. So the approach to transform this more abstract model into a model that can be directly realized into relational tables is to make in-place transformations, which similar to refactoring operations. And the first operation to be applied is that we get the non-sortals and we flatten them out. That's the way we call this operation. Now, flattening means that we take the attributes of the classes and the associations in which they're involved, and they are pushed down in the direction of all the subclasses that they have. And then we take those subclasses of kinds, which are all the sortals in the model, and from the bottom, from the leaves, we lift them up in the direction of the kinds. Again, this means that attributes get refactored into their superclasses, and here we have the interesting thing that different from other strategies, that because kinds, they partition all the domain, that we end up not having problems with multiple inheritance. So let's work this approach through the running example so that you can see the effects of these operations. So first, here we have the flattening of the non-sortals in the model. Now this means that attributes, as I mentioned, they will be refactored to subclasses, here person and organization, subclasses of name hierarchy, and the named entity, and personal customers and corporate customers will, as customers, receive credit rating attribute, and also the association ends attached to the superclass end up being attached to the subclass with some changes in cardinality that are required. So here's the resulting model with all the non-sortals flattened, and then we proceed by lifting the sortals in the direction of their kinds until the kinds are reached. So here again we have that attributes, they end up being pushed in the direction of the supertypes, with the cardinality, the lower bound of the cardinality, being relaxed because not all adults are personal customers. So these cardinalities have to be relaxed, the association ends have to be moved accordingly, and in the case of many of those classes, attributes in the superclass are created to inform whether they are an instance of the subclass. So here we have is employee, here we have is contractor, and is corporate customers, which are Boolean attributes to indicate this status. And the cardinalities have been adjusted accordingly. Now we have other sortals in this model, so we're still lifting sortals. And here I just want to exemplify what happens with the generalization sets when we lift sortals here. So here we have generalization sets with different meta properties. And what we'll do here is that we'll generate discriminators for the types, because when we lift child and adult, not only the attributes will be lifted, and as I mentioned, the association ends. But also we need to know which persons are child and adult. We need to know the person's citizenship, or whether the organization is a primary school or a hospital. So in this step, we introduce those enumerations corresponding to the generalization sets, and the cardinalities. They end up reflecting whether there's disjoint or complete, or disjoint and incomplete, or overlapping complete, overlapping incomplete generalization sets. So now we have a model which only has classes corresponding to kinds and those enumerations here. So we are ready to transform this into the relational model. So here, basically, this is exactly the structure that ends up in tables with keys to represent those associations here. See that there are no end-to-end associations because of the use of relator kinds. So the relator kinds, they refine those relationships here. So we end up having solved already the problem of end-to-end relationships. So we don't need to introduce any additional tables. This is the model as it's realized in the end. If we compare, so you can find in the paper comparison with other approaches in terms of performance. So our approach, the one table per kind approach, it has a number of tables corresponding to the number of kinds. Other approaches have tables corresponding to the, for example, the total number of classes in the source conceptual model. And the number of kinds is typically, from our statistics that you can find in the paper, typically 1/4 of 1/5 of the number of tables per class. But most importantly, we now don't have those performance penalties that we have, for example, in the one table per class approach. We can deal with multiple inheritance, dynamic classification, and orthogonal generalization sets. And we also have now a good performance in terms of whenever you need to do polymorphic queries in the model, which are those queries in the end that will refer to the non-sortals in the model. So we have been able to show the benefits of using these ontological distinctions to guide the transformation with this one table per kind approach. This goes beyond what can be achieved with the strategies that are ontologically neutral. So when we realize that the classes have different properties, we see a way to make a transformation or realization of the model which has better performance and which solves the problems of supporting the primitives in the conceptual model. Now we have a working implementation of a transformation from OntoML to OWL that we can use as a basis for ontology-based data access. So this relational models that we show can be accessed through semantic web ontologies, with giving the user a higher level access to the relational data. We are planning some empirical evaluations of the approach. We're mainly concerned with whether people would be able to write and read and understand those queries better, and also understand the relational schema that's generated better. And we believe this is the case. We hypothesize this is the case because object kinds are very important in human cognition. So we have good reasons to believe that this approach will be better. Okay, I welcome now questions.